Today we will learn about crystal field theory. Crystal field theory is a theory explaining about bonds between metal and ligand by introducing a new concept, splitting of d orbital. Before we start discussing about crystal field theory in depth, let's get to know what d orbitals are. D orbitals have angular momentum quantum number L being 2 and 5 different magnetic quantum numbers. Therefore, there are total 5 d orbitals and they look like these. Except for the dz square orbital, they have 4 lobes along the certain planes. dxy, dyz, dzx have lobes between each axis, while dx square minus y square have lobes on the x and y axes. By these different shapes, the crystal field theory arises. Now the crystal field theory begins with ligands bonding to the center metal atom. Since ligands make a coordinate covalent bond with the metal by donating an electron pair, this theory assumes this bonding rather having ionic bond properties. Since the d orbitals have different geometry, they have different energy by the electron environment. Let's first consider about an octahedral environment case where the ligands bond through the octahedral positions along the x, y, z axes. dx square minus y square and dz square orbitals align through the x, y, z octahedral axes, while dxy, yz, zx are rather off the main direction. Therefore, dx square minus y square and dz square orbitals have higher energies than the other 3 orbitals. The upper 2 orbitals are called Eg and the lower 3 are called T2g. The energy gap is called delta O, where O stands for octahedral. Eg orbitals are higher than the degenerate position by 3 out of 5 delta O, and T2g are lower by 2 out of 5 delta O. Now let's think the electron configuration in these orbital environments. The biggest difference with the degenerate case is related with the Hund's rule. When electrons are configured in the orbitals, they tend to stay alone, then pairing with another. Considering Hund's rule, unpaired electrons will fill T2g and Eg orbitals first, then start pairing. This case is called high spin. However, if delta O is too large, the pairing electrons in T2g orbitals requires less energy than staying unpaired in the Eg orbital. It will fully fill the T2g orbitals first, then fill up the Eg orbitals. This case is called low spin. There is another concept called crystal field stabilization energy. It stands the amount of energy that are split by the ligands compared to the degenerate state. For octahedral case, crystal field stabilization energy is equal to the number of electrons in T2g times minus 2 out of 5 delta O plus number of electrons in the Eg orbitals times 3 out of 5 delta O. This table shows the crystal field stabilization energy for each D1 to D10 materials in the octahedral case. If you carefully look, high spin D5 and D10 have crystal field stabilization energy value of 0. Therefore, high spin D5 and D10 materials are especially more stable.
In the case of square planar crystal field, you can see ligands are coming from 4 directions, each on the x and y axes. So energy on d orbital are degenerated into 4 different levels. dx squared dash y squared has the highest energy, and dxy will be the second highest energy, and dz squared will have the second lowest energy, and dxz dyz has the lowest energy. One key point of this particular crystal field is that the energy gap between first 2 energies is same as the one in the octahedral crystal field. By this phenomenon, not only square planar complexes but also D8 ligand tends to have square planar crystal field rather than octahedral or tetrahedral due to high stability. The last one is tetrahedral crystal field. There are 4 ligands attached to the central metal in the diagonal way, and that will leave dxy, dyz, dzx the highest energy and last 2 with the lowest energy. Let's label each level as T2 and E. The energy gap of tetrahedral complex is relatively smaller than the one in the octahedral, about 0.44, which is the reason why tetrahedral complexes are usually high spins. And if you look carefully, there is no G on the each energy level, and that is because they don't have inversion symmetry, as you can easily find by drawing. However, CFT has limitations. There are mainly 2 limitations, which is it can't fully explain the spectrochemical series and it only takes d orbital into account. So, What is the spectrochemical series? There is an order of ligands by delta O called spectrochemical series. This is the common spectrochemical series, and the ligands on the right side is much stronger than the left side. If you look carefully, H2O, CO, and H3 like neutral ligands have larger delta O than negative ligands, and CFT can't fully explain this, especially. This phenomenon means that the interaction between metal ligand is not purely ionic, which is reverse of the assumption of CFT. Also, the theory only takes d orbital into account, which actually s and p orbitals also does relate on complex formation. And by those, there is new theory called ligand field theory to handle those limitations. And this is the end. Thank you.